Okay, so I didn't give any homework in this class either, right?
No.
Right, we had the test. So last time was Wednesday, and I brought up the TDS equations. So we have TDS is equal to du plus PDV. And remember, these are all intensive, I mean.
Dependent on mass.
Yeah, they're all per mass, exactly. So these are all the values that you can find in a table. And then the other one is TDS is equal to DH minus VDP. And basically, we will always just use these in cases where we can make simplifications. We did do the one simplification that said for incompressible materials, the change in specific entropy is equal to the specific heat times the natural log of the later temperature divided by the earlier temperature. And remember that these have to be absolute temperatures, so we'll do these in Kelvin. So let's see how good an approximation this is in real life. So let's calculate the change in specific entropy for liquid water. We really can only do this for liquid because we're assuming incompressible. That goes from 30 degrees Celsius to 80 degrees Celsius at 10 bar of pressure.
So TDS is change in temperature with respect to entropy?
It's just, it says at every state, at every instant, the temperature at that instant times whatever your change in entropy is has this relationship with the other stuff. So anything that's not a D is saying that's the value at that instant, and the D's are saying these are the directions things are changing, or the amounts things are changing. Okay, so we're going to do this using this approximation for incompressible, using the TDS equation. And then we're going to, so like this is part A, and then we're going to compare to what you get in a table and just see how close it is. So first, we want to look up the specific heat for liquid water in the correct temperature range. And I think the value that's given is 50 degrees Celsius, and we'll use that C is equal to 4.18 times 10 to the third joules per kilogram Kelvin.
And that doesn't change all that much?
Not very much. Not very much for incompressible. It pretty much just changes from about 4.18 to about 4.22. And So now we'll put this into the equation that we got last time and calculate that the change in specific entropy is equal to 4180 times the natural log of our T2, our temperature 2 is going to be 80 plus 273, so 353. That's 80 Celsius expressed in Kelvin. And then we're dividing by 273 plus 30, so 303. And
Glad I came.
okay. All right, so these are things you just look up, and you can see where this comes from. I'm not going to go through this derivation, but this comes exactly from this equation 2 star. We're just integrating all these parts. This difference in this S0 at T2 minus S0 at T1 is just this full integral of this first term, where you're taking into account how CP changes over temperature. You with me on that? Okay, so let's do.
So what you're saying is someone else has already done that math and they put it in the table.
That's right. Yeah, exactly. Yep. All right, so let's do this for air. And we'll say that at temperature 1 is 300 Kelvin and pressure 1 is 1 bar. And it's going to a state 2 where temperature 2 is 1000 Kelvin and pressure 2 is 3 bar. And we want to calculate the change in specific entropy. First, assuming that Cp is a constant of 1.005 times 10 to the third. We're assuming that it's constant. And then second, using the S0 values from the air ideal gas table. Okay, well, using this S0 is always going to be more accurate because it's taking into account that CV and CP are changing over temperature ranges. The problem is we don't have ideal gas tables for every type of gas. In this case, we do. We have one for air, but we can come up with a reasonable approximation in most cases for a gas that we don't have an ideal gas table for. So remember that this is the one that's always more accurate if you have the table. Okay, so delta S is equal to Cp times dt over T minus R times dP over P. And I'm using this form because we're given pressures, we're not given volumes. So you're just using whichever one has the values that you have. So the change in specific entropy is equal to 1.005 times 10 to the third. This is all in SI units. times, well, sorry, let's go through the integrals. So we have the integral of, we're assuming CP is constant, so you can pull that out. That's the key to this approximation from state 1 to state 2 of dt over t, minus r is always constant, so you can pull that out, times the integral from state 1 to state 2 of dp over p. And so now the change in specific entropy is equal to Cp times the natural log of temperature 2 over temperature 1 minus R times the natural log of pressure 2 over pressure 1. And so now we can plug these in. So this is 1.005 times 10 to the third times the natural log of, these have to be in Kelvin. That's how it was given in this problem. So it's 1,000 divided by 300 minus an R of 280. I think I usually use 289, but I have 287 here, and that's what my calculations are using, so I'll use that. Times the natural log of, this is 3 times 10 to the fifth over 1 times 10 to the fifth, so that's just the natural log of 3 if you cancel stuff. And so specific change in entropy is 894.7 joules per kilogram Kelvin.
The change in entropy from pressure 1 to pressure 2 is that?
Yeah,
Got it.
right. The temperature went up and the pressure went up. Okay, so now we're gonna use the form, this one, which is gonna be the more accurate one, and just take values out of the table that we just happen to have. So this time, the change in specific entropy is S0 at 1,000 minus S0 at 300 minus 287 times the natural log of 3 times 10 to the fifth over 1 times 10 to the fifth. You might have to do interpolation if 1,300, and if you're starting and ending temperatures are not values that are given in the table. So that's an extra pain you might have to deal with. But in this case, we get 2.97 times 10 to the third minus 1.702 times 10 to the third minus 287 times the natural log of 3 and you get 952.7 joules per kilogram Kelvin. So as a first order approximation, it's okay. That's a huge, notice that the range of temperature and pressure we use, that's a huge range in temperature and pressure, and we still got something enough in the ballpark to be helpful in a estimate, and the smaller that range of temperatures and pressures is, the closer those will be to each other. I guess actually the range of temperature, the pressures doesn't even matter. It's just how much the temperatures are varying. So even though This is a huge temperature range, a huge delta T. We got kind of okay results.
And so, like in the real world, if you were trying to calculate something to design a system and you have limited information, would you just take that like 850-ish or 890 number
Right.
and you would just say, okay, I'm going to make it like be able to withstand like 1,000?
I think it just always comes down to how much precision you need for your calculation. You just need to keep in the back of your mind, like, this is a useful approximation over a big range of temperature ranges. But the bigger the temperature range is, the less I want to trust that value. That's all. Any other questions about that? Okay, the next thing we're going to talk about is entropy produced. You can think of this as a measure of inefficiency in your system. Um, and I'm just going to give you, I'm not going to go through this derivation. We'll talk about it after I give you this, but the change in extensive entropy is equal to the integral from state 1 to state 2 of your delta Q over T all the way around the boundary plus some value sigma. This integral is for your actual process. And this sigma is the entropy produced. Okay, so where does this equation come from? We can sort of make sense out of it because notice that we said, so the Clausius inequality, okay, says that this is going to be, well, it says for a cycle, okay, but let's think about it in terms of a cycle, okay. The Clausius inequality says that this is less than or equal to 0, okay, but it's equal to 0 if the cycle is reversible, okay. The way we defined the change in entropy is using this integral for a reversible cycle, okay? So if you have a reversible cycle, then this is 0 and this is 0, and so the entropy produced is 0. If you have perfect efficiency, this sigma value is 0, okay? If you don't have perfect efficiency for a cycle, this is going to be less than 0. This is still going to be 0. And so your sigma is going to be some positive number. Okay, so this is like a relationship between the Clausius inequality, sort of, and the definition of entropy. Well, it deviates from that in one kind of important way. The Clausius inequality only dealt with cycles. This is saying this is true from any state to any other state. Okay. Um, so this is basically relating the Clausius inequality to the integral definition of entropy but it's not requiring that the process be a cycle. Okay, so let's go back to, this is a problem we did before with a gearbox. So here's the gearbox. Um, and we had 60 kilowatts of power coming in to this shaft, and 58.8 kilowatts of power coming out the other shaft. And this is a steady state process. And the temperature of the boundary is 300 Kelvin. What's the entropy produced? Well, we know we're going to use that integral form that I just gave you, this boxed equation. And so we're going to have to come up, in order to use this, we're going to have to come up with how much heat is lost. It's steady state. So we have this form that says, we have everything in terms of differentials. So we have d dt is equal to q dot minus w dot. It's steady state, so this is 0. And so q dot is equal to w dot. W dot, now remember, W is positive if the if your system is doing work on the surroundings. So in this case, you know, we have the work coming in here and work leaving here. So the positive is going to be the 58.8 kilowatts. The negative is going to be the 60. So we have 58.8, I'll do it in SI units, times 10 to the third, minus 60 times 10 to the third. And so W dot is equal to negative 1.2 times 10 to the third watts. And so that says that Q dot is also equal to negative 1.2 times 10 to the third watts. Does that make sense that Q is negative here? Positive Q means heat coming into the system. This is just a case where these things are heating up and that heat is being lost to the surroundings. So we would expect it to be negative. And now we can go in and use that integral definition. So delta S is equal to the integral of delta Q over T around the boundary plus sigma.
And when you say it's heat is getting lost to the surroundings, is that like the air around the gears?
Yeah. The air around, so our system is the entire box, and the boundary of the box is at 300 Kelvin, and so we're talking about heat being lost into the air outside the box.
Got
it. Okay, so what can we simplify here? We have this integral in sort of a funny form. We have this delta S. But this is kind of in a form where we can't use any tables or anything. Okay, well, we know that it's steady state. So what does steady state tell us about this?
The first term is 0?
Yeah, any properties in steady state are unchanged. And so this goes away because it's steady state. Okay, and now we can think of so in order to use this, we have to have a state 1 and state 2. So anytime you're in steady state, like any amount of time is a cycle. Okay, so let's just use 1 second. Stupid computer. So in steady state, any time interval is a cycle. A cycle just says the properties, return to the same value. All the properties return to their starting value. Well, in steady state, they always stay the same value. So does that make sense to you? Let's just use 1 second. And so we get 0 is equal to the integral of dq is negative 1.2 times 10 to the third divided by the temperature, which is 300 Kelvin. And we can get rid of that integral. So this is the integral. It's the total amount of heat divided by the temperature plus sigma. And so sigma is equal to 4 joules per Kelvin every second.
Because of our imaginary 1?
Yeah, right. We did that just so that we could use the values that we had in watts as energy amounts. And so now you could also write this as, what this says is that the rate of entropy production is 4 watts per Kelvin.
And that's how inefficient we are.
Yeah, that's right. So if this was totally reversible in this case, since it's in steady state, we would be producing 0 entropy.
And all of those 4 watts are being lost in the form of heat?
Yeah. Heat is what always produces entropy, heat transfer.
Got it.
Yep. Remember, entropy is defined in terms of heat transfer across boundaries. And so yeah, remember the thing, it like relates to the, so every time heat goes from a high temperature location to a low temperature location, the usefulness of that energy is going down. Right. And that's really what entropy production is. You're making energy less useful.
Because we keep having to lower the temperature to
of,
get any...
Right, of the exhaust.
Yeah.
In order to get useful work out of it. Yep. Okay, so the next thing we're going to do, so what are the benefits of entropy? It lets us calculate efficiencies in systems, and it also, for the first time, lets us determine the directionality of processes. And so I'm going to stop here for today, but next time, we're going to use entropy to determine the possible directions of processes in time. And so I gave you, like when we started talking about entropy, I gave the example of the skier. If it's everything's perfectly frictionless, this skier could go down this big hill, circle around at the bottom. He's still not losing any energy, ski right back up to the top of the hill, you know? And so using conservation of energy, you could do this calculation and figure out how fast he's going to be at the bottom. Or you could use how fast he is at the bottom and figure out how high he's going to get on the hill. And there's no difference between those. Conservation of energy can't tell you anything about which one of those things happened first or second. Okay? But with entropy, we're going to be able to figure that out. Okay? So like the example that I think I'm going to do here is if you throw a hot piece of metal into a water bath, okay, a cold water bath, the temperature is going to come to some equilibrium. Conservation of energy, the first law of thermodynamics, doesn't say anything about which is the first state or the second state. According to the first law, you could totally plausibly put metal and water together that are the same temperature, and tons of energy would flow into the metal, out of the water, and you'd end up with a hot piece of metal and a cold water bath. But obviously, we know that's impossible. And entropy is how we're going to show which one of those is a possible direction and which one is not.
And is that the science that's going to tell us that?
Signs? Yes, because that entropy produced has to be positive.
Got it.